Hi folks, in the last part of this week's lesson, we're going to take a look at two more examples where we have three planes in which none of them are parallel, but we don't necessarily have a single solution to the system. All right, and if you think back to all the possible scenarios with three planes, you remember that there were two scenarios that involved three planes where none of them were parallel, but where they didn't intersect in a point. So we'll see what happens here. So as usual, when I take a look at a system of equations, I should be looking at the three normal vectors and testing to see if any of them are parallel to each other. But I can see very easily by looking at the three normal vectors, the A, B, and C, that none of them are parallel. Okay, so let's just recall what our strategy is for solving this type of system. Okay, so that's not going to change. What we're going to do is we're going to start by using two equations to eliminate a variable, and then use a different pair of equations to eliminate that same variable. And that's going to give us a system of two equations and two unknowns, which I know how to solve. Okay, so let's do the easy one first. So again, you'll notice and you'll see sort of next week why I tend to work with x as much as possible, but it's a nice and easy one anyway, so I might as well work with it. So I'll start by using equations 1 and 2 to eliminate the x variable. So we'll do 1 minus 2. So equation 1 minus equation 2, so x minus x is 0, as expected. 1 minus negative 1, so 1 plus 1 is 2, so we have 2y. And then here we have 2 minus negative 4, so 2 plus 4 is 6, so plus 6z equals, and then here we have 6 minus negative 2, so 6 plus 2 is 8. All right? So now, one thing that I did in the previous video is why don't I make my life a little easier here and divide both sides by 2, okay? Because again, legal operation doesn't change the equation to divide both sides, so might as well do that. So y plus 3z equals 4, and I'll call this equation 4, okay? So let's now eliminate using equations 1 and 3. Okay, so here I'm going to have to multiply equation 1 by 3. Okay, and then I'm going to subtract equation 3. Okay, and let's see what happens. So 3x minus 3x, as I expected. Okay, this is going to be 3y minus 5y. So 3 minus 5 is negative 2, so negative 2y. And then here we've got 3 times 2 is 6, minus, sorry, I lost myself. Oh, yeah, I'm doing 1 and 3. So 3 times 2 is 6, minus 12 is negative 6z. And then here we've got 3 times 6 is 18, minus 27. So let's just, let's just be certain, but I'm pretty sure that's negative 9. I don't think I need to check that with the calculator. Okay. And so now, lo and behold, I look at this here and I probably didn't need to simplify it, okay? Because I see that I've got the 2y and the 2y, it's actually better to work with that equation there, okay? So I was maybe a little quick to simplify this here because this is actually going to be easier to solve working with those two equations. So I'll call this equation 5. And if I want to eliminate now the y, I'm just going to add equations 4 and 5. Okay, so let's see what happens. 2y plus negative 2y, so 2y minus 2y is going to give me 0y. And you might be wondering, why is he writing that down? I think you'll see in a second, or maybe you already see it. Okay, 6z minus 6z, that's going to give me 0z. And then here we have 8 minus 9 is negative 1. So essentially, what I've come to is that 0 is equal to negative 1. Okay, that's a problem because this is a contradiction. 0 is not equal to negative 1. Okay, so we have to ask ourselves, what does this tell us about the original system of equations? Okay, so by looking for an intersection, it means we're assuming that there's an intersection between these three planes. And if that results in a contradiction, okay, if doing all this work correctly results that 0 has to be equal to negative 1, well, I know this can't be true. So what is the conclusion? The conclusion is that there is no intersection. Okay, therefore no intersection, or I guess in this case here I'm just looking for the solution to the system, so I should say no solutions. Okay, now what is the geometric interpretation? Okay, so the geometric interpretation is, well, there are no points of intersection, but we can go further than that, okay? Because we know that none of the planes are parallel to each other, so there's only one scenario where there's no intersection and the planes are not parallel, and that's the scenario of the triangular prism. So again, you have to remember, this is a cross section. So you have one plane coming out here, another plane coming out there, another plane coming out there, and they create this triangular prism. Okay. So that is the geometric interpretation. Okay. Now, what's nice is that without necessarily having a sense that it would come out this way, the algebra brought us to that conclusion. Okay, so what I want you to notice here is that my strategy for solving was exactly the same, except the conclusion that we came to was different. In this case here, because it resulted in this contradiction, the conclusion is that there's no solution and that clearly it must be this scenario where there's no points of intersection. All right? Excuse me. Let's take a look at another example. Okay? Let's take a look at this system of equations. And again, take a quick look at the normal vectors and you should see that there's no parallel normal vectors. Sorry again. So I know I don't have any parallel planes. Okay, so let's do what we did before. So here, well, I'm definitely going to work with the x's because that's a lot easier. So let's start by eliminating the x's from equations 1 and 2. So 1 minus 2. So x minus x is 0. Negative 3 minus 11, that's going to be negative 14 y. Then here we've got negative 2 plus 5 is going to be plus 3z. And then here, oh, sorry, we're subtracting. So negative 2 minus 5. Sorry about that. I'm glad I caught that early. Otherwise, that would have made a big mess. Negative 2 minus 5 is negative 7z. And then here we have 7 minus negative 5. So, 9 minus negative 5. So 9 plus 5 is 14. Okay. And that actually works quite nicely. Okay. So last time I was a little too quick to simplify this, so I'll leave myself a bit of room in case I do want to simplify it, but I think for now we'll leave it as is. Okay, so now let's use equations 1 and 3. So I'll do 2 times equation 1, and then I'm going to subtract equation 3. So 2x minus 2x is 0. Okay, this is negative 6y because I'm multiplying by 2 plus 8. Negative 6y minus 8 because I'm subtracting, so that's negative 14y. Okay, so it's actually a good idea not to simplify. All right, here we've got negative 4 minus 3 is negative 7z. Oh, it's looking interesting. Okay, and then here we have 18 minus 4 is 14. Okay, so when I look at equations 4 and 5, and, let's say I tell myself I'm going to eliminate the y values. So I'll do 4 minus 5. Well, negative 14 minus negative 14. So negative 14 plus 14 is 0. Okay. Negative 7 minus negative 7. Negative 7 plus 7 plus 0z. And then 14 minus 14 is 0. And what we end up with is 0 equals 0. Well, what does that tell me? For what values of y and z is 0 equal to 0? Any values. This is always true. So what's the interpretation here? The interpretation is that there must be infinitely many solutions. But let's recall what that tells us geometrically. Okay, how did we have three planes with infinitely many solutions? Well, it's when they all intersected in a line, when there was no parallel planes. Okay, so yes, this tells us that there's infinitely many solutions, but we know that that should be forming a line. So we should be able to determine what those solutions are. So our conclusion, okay, is we have infinitely many solutions. Okay. Geometrically, we know that the planes intersect in a line. But of course, we can go further. We can actually say exactly what those points are. Okay, so what we have to do is we have to come up with the equation of a line. But remember that the way in which we determine the equation of a line with these planes here is by writing two of the variables in terms of a third. And take a look at this equation here. Okay, from equation 4, I'm able to write, well, I think it's easier to solve for z. So let me bring z to the other side of the equation. So 7z, and here I've got negative 14y minus 14. So z is equal to, divide by 7, negative 2y minus 2. Okay, and what I've been able to do here is to write z in terms of y. Now what I want to do is I want to write x in terms of y. So I'm going to take this and I'm going to plug it into one of these equations. I think number 1 looks to be the easiest. Okay, so here if I take equation 1, I have x minus 3y minus 2 times, well, wherever I see z, I'm just going to replace it by negative 2y minus 2. Okay, and then that's equal to 9. And let's clean this up here. So x minus 3y, this is going to be plus 4y, this is going to be plus 4 equals 9. So x is going to be equal to, so negative 3 plus 4 is 1. Bring that to the other side, negative 1, so negative y. And then 9 minus 4 is 5, negative y plus 5. So what have I managed to do? I managed to write z in terms of y, x in terms of y. So I'm going to let y be my parameter. So my solutions are given by, well, x equal to negative t plus 5, y equals t, and z equals negative 2t minus 2, where t can be any real number, which, of course, we remember represents the equation of a line. Okay? So, last time we worked on systems where there were no parallel planes. Okay? In those previous two examples, we saw that they both intersected in a point, and so we were able to solve for each variable one after the other. Here, it turns out it wasn't the case that there was a single point of intersection, but the algebra showed us the way. In this case here, we ended up with this contradiction, which told us there had to be no solution. Hence, the only option was the triangular prism. In this case here, as we were solving, we ended up with a statement which is always true, which told us that there was infinitely many solutions. So the only option was that the three planes intersected in a line. Okay, but of course, to find the equation of that line, to find those solutions, we just followed the method from before, which is to write two of the variables in terms of the third, and that third then becomes your parameter. All right, that's it for this week's lessons.